Welcome back. We left off at the break with the preliminary vehicle sizing. This is sort of the summarization or last chart on that. If you look at Krieger's notes, you can do this for yourself in your own time. You can combine terms that he has there and come up with this equation for a length scale factor that I call F sub L. It's a function of kV, one of the geometric parameters, fuel density, the unit weight of the structure, which I took looking at the graphs. It looks like our baseline vehicle was down in the range of 3 pounds per square foot. So I continued to use that throughout. But as the vehicle scales up, you can see from his curves that that unit weight actually goes up, and I just sort of neglected that. Propellant fraction, we already established at about 0.6. Total volume of the original baseline vehicle, plan form area, wetted area, and in your notes, this exponent was neglected. You might want to write that in. Anyway, for our geometric parameters of 0.47 and a unit weight of 3, propellant fraction of 0.6, our scaling factor came out to be 1.9. So our 1,000-inch aircraft went to 1,900 inches. Now we should be in a reasonable ballpark in terms of the vehicle size. I already talked about why sizing is important here, and down at the bottom here just shows what the new volumes and areas are. You can see our volume went up substantially to about 23,000 cubic feet, and our takeoff gross weight is now setting at about 146,000 pounds as our starting point. Okay, I'm going to move on. Now we've sort of established our baseline design, the thing that we're going to key off of here. I'm going to get into some of the issues, and I'll start with low speed and we'll work up in Mach number. At takeoff conditions, our drivers are basically lift, being able to take off for such a heavy vehicle. Body lift, the body's large as you saw in our design. You get both linear and nonlinear lift on that body. Wing size, you will need a wing. Trim is a driver, and ground effects, both powered and unpowered. There are many contributors to low-speed lift. Number one, there's camber. Now, even in our body, our wing won't be cambered, not very likely, but our body's cambered. Camber being, if you take the mean line of the body, you can sort of trace my pointer here and see that it's negatively cambered. Well, at high speed, that's great. At just wedge theory, you get lift off of that. Low speed gives you negative lift. Okay. Aspect ratio is an important driver. We do have low aspect ratio shapes for obvious reasons of drag. Vortex lift is a contributor, and ground effects I mentioned. Okay, in the linear lift area, airfoil thickness is a contributor. I have a theoretical equation for airfoil thickness here, airfoil thickness effects on the lift curve slope. It's basically a function of thickness to chord ratio, but on real airfoils, the thickness effect is influenced by trailing edge geometry, and I've neglected the reference here, but it's basically it's the Air Force DATCOM that has some graphs, and that DATCOM is referenced in the back, but it's that where you can get some of the effects of the trailing edge. Airfoil camber, I mentioned. Down here I have a camber effect term that I've derived by assuming a camber distribution. And actually, if you look at experimental data like Abbott and von Donhoff for actual airfoils, turns out that this contribution to camber compares pretty well with the experimental data. Wing aspect ratio is well known and well understood. It's a function of the aspect ratio of the wing. The lower the aspect ratio, the lower the lift curve slope, and also a function of the plan form efficiency, where that efficiency is 1 for an elliptic lift distribution and less than 1 otherwise. Typically for the kinds of shapes we're talking about that are very sort of rectangular or flat plate, like efficiency factor of about 0.5 is reasonable. Now, nonlinear lift. For highly swept, low aspect ratio, slender bodies, you get leading edge separation. That leading edge separation produces vortices that roll up on the upper surface, and as you can see from this pressure distribution across the span of a delta wing, you get these pressure peaks, actually negative or suction peaks, that do contribute to lift. Down below, you'll see your typical linear lift, that's your sort of 2 pi alpha contribution to lift, and then the nonlinear part that can be quite substantial. Over to the left, you'll see different, if you could hone into the left there, rectangular wings, delta wings, and cones all produce this kind of effect. And our body shape is somewhat like that rectangular shape there. Another piece that contributes to that nonlinear lift is cross-sectional shaping. This is from a recent AIAA paper where 3 different cross-sections were tested for this ogive body. One was circular, another was elliptic, and then there was this chined body. The chine should remind you of an SR-71 or an F-16. You can see from these lift curve slopes to the right, this is normal force coefficient as a function of angle of attack. You can see that the chined bodies, which must have produced stronger vorticity, substantially increase that nonlinear lift. So there's a lot of things you can do with shaping your body to enhance that nonlinear component of lift, which could potentially, say, downsize your wing requirement. The wing, you'll find, as you go to higher and higher speeds, it's needed less and less. You get centrifugal relief on the vehicle. You know, your V squared over R term, as V goes up, there's much less required lift. You don't need the wing so much. You don't want to carry that as extra baggage on board. It's just weight, it's friction drag, pressure drag, wave drag, all that. You don't want to carry it if you don't have to. Okay, this very briefly is just some data, some actual data, and then correlations of the data coming from Kukuman. The correlations are shown on the screen here. It's lift curve slopes for rectangular wings, similar to our shape. There's the linear part, sort of a classical linear term, and the nonlinear parts, both for a thin wing and a thick wing. And ours would be more like a thick wing. Over on the right, you do see the data that supports that. Similar data and correlations are shown here for delta wings. It also points out a thickness effect having to do with the leading edge. Basically, the leading edge angle is the correlating parameter there. So for a delta shape, and our wing that our actual wing might be more delta shaped. And then lastly, just briefly, anhedral and dihedral do impact that nonlinear lift. And you can pick that out pretty well from that data. Now another could be very important contributor to lift is ground effects. Most aerodynamicists are pretty familiar with just the classical unpowered ground effects of having a trap vortex near the ground. But engine flow, powered ground effects can also be very important. The engine flow is on the lower surface of the vehicle, at least in our baseline design there, and it can increase or decrease lift depending on how close you are to the ground and angle of attack and other things like that. Some different theories for why that might be. There could be a Venturi effect for subsonic flows, or if the flow is supersonic, you could get supersonic overexpansion effects that tend to suck the back end of the plane into the ground. I already mentioned what it's a function of. A lot of testing has been conducted at NASA Langley on a generic NASP shape to try to quantify this effect. The model that they tested looks like this, a very simple shape with a pointed planform nose there. It does have a propulsion package on it. For this model, the propulsion was provided by little ejectors inside that duct there that just basically entrain flow through the flow path. This data is courtesy of NASA Langley and Greg Gatlin at NASA Langley. I want to show you a color slide here. I hope it shows up because it is on view graph form. If you could shine down on this, please. Come over. Well, that doesn't show up well at all. we don't have our light table. But anyway, there's the configuration, and this is a laser sheet being shown through the propulsive stream. And those in the class can come and look at this at break. I apologize for that not showing up. Moving on to some of the data that's been gathered there. Point out this coefficient of thrust. Coefficient of thrust is defined as the static thrust, means the thrust of the propulsion system without any flow going around it, just sitting statically, over dynamic pressure and a reference area, here being the planform area. Plotted are moment, lift coefficient, and drag coefficient as a function of the height of the vehicle away from the floor divided by the span of the vehicle, and for different values of thrust coefficient, going from 0 up to values of 0.8. And concentrating on the lift, since we're talking about powered ground effects here with lift, you'll notice that a 0 thrust coefficient actually gives you positive lifting effects close to the ground. That's the unpowered. Then as you go to higher and higher thrust coefficients, eventually you get into this regime where the powered effects at a fixed angle of attack are negative and tend to suck you into the ground. That was as a function of thrust coefficient. This data here, shown here, is for a given thrust coefficient, okay, of 0.4, and at different angles of attack. And what's interesting here is at lower angles of attack, around 8, you get that negative lift powered ground effect. And then as you eventually get to higher angles of attack, you actually, the trend changes and you get to down close to the ground here of positive ground effects. So this is an important consideration. It's dictated by how close you are to the ground, what your thrust coefficient is, what angle of attack you take off at, a lot of different drivers. Okay, in the next couple of pages, which I don't have a whole lot of time to develop, I've done a takeoff lift analysis, and you can work your way through that. Included all the pieces, the basic body lift and the aspect ratio effects, the camber effect, and I have referenced all these things, so you can go back to the original sources if you have a desire to. Camber effect, the nonlinear lift term, this is for our body. This isn't for, we haven't even put a wing on our plane yet. We're just looking at the body. We've sized the body, we've dimensioned the body. This is the lift on that body, which you'll see becomes very a big portion of the lift. Okay, looked at powered ground effects using that test data. For our thrust coefficient, in a moment I'll talk about how many engines we have and what thrust we have at takeoff. But for 2 engines, you'll see how we get to 2 engines. We have a thrust of 71,000 pounds. For the dynamic pressure at takeoff in our planform area, our thrust coefficient is pretty low. Okay. To avoid, if you lower the camera there a little bit, to avoid tail scrape on the configuration, we can't exceed an angle. Here, let me just slide this in. There we go. Note that our baseline vehicle had what I call a chordal angle. That's just the average angle from the beginning of the nozzle to the end of about 13.7 degrees. It just was a fallout of the way I geometrically laid it out. So I limited the takeoff angle of attack to 13 degrees. For this angle of attack and thrust coefficient, that Langley data showed no lift increment due to powered ground effects, approximately 0. So we ignored that effect. Therefore, going down here, using the equations derived there for lift coefficient, at 13 degrees we get about 0.13 lift coefficient, and that relates to a lift over dynamic pressure of 652. For our weight of 146,000 pounds, that means that we have to be flying at a dynamic pressure of 224 psf, and that corresponds to a 258 knot takeoff speed. Without wings, our body will take off at 258 knots at 13 degrees angle of attack. So we'll take that as our preliminary takeoff speed, not even considering wings yet. This is just an interesting comparison. We'll talk about wings more later and why you need them to take off, at least if we can take off at that speed. Now that the speed at which you take off is a function of tire technology, really. Can you have tires that can withstand those kinds of velocities? Shown here, just for illustrative purposes, are our calculated lift curve slope for our baseline body, shown by the squares here, versus angle of attack, that's lift coefficient, and then just an equivalent cone vehicle. As you can see, the cone vehicle is uncambered, but our shape, our baseline shape, is not. So we initially have a negative lift coefficient at 0 alpha, but as you increase the angle of attack, that strong nonlinear lift actually crosses over and we have higher lift coefficients than the cone. Plus, I should point out that the cone has substantially less planform area, so the actual lift would be less as well. Okay, takeoff thrust analysis. Need some idea of what the thrust needs to be. Well, how do you what's your starting point? Typically, you look at a thrust-to-weight ratio, the thrust over the weight of the vehicle. So I looked at some historical data. The XB-70, which was a Mach 3 bomber, basically, built by North American Rockwell 20, 30 years ago, had a value of 0.32. And the Concorde SST had about 0.39. So I assumed a value of 0.32 corresponding to the XB-70, which meant that we had to have at least 46,000 pounds of thrust to get that kind of thrust-to-weight ratio. For the Pratt & Whitney F100 PW100 turbofan engine that I mentioned earlier, which weighs about 2,800 pounds, okay, using that piece of information, and from that data that I showed you for our advanced turbojet, at sea level static conditions, the engine produces a thrust-to-weight of about 10. So 10 times 2,800 is 28,000, which would dictate a minimum of 2 engines to have a reasonable takeoff capability for a plane. So we've started there. We'll find out later that at the thrust, the transonic pinch point, that's not going to be big enough. We'll have to increase that. But for now, that's all we know. That's all we've done. So we've got 2 engines producing about 35,700 pounds of thrust at Mach 0.4. The thrust does increase as you increase your speed. So, and we've already determined that our 275 knots was a takeoff speed. Okay. Just briefly, don't want to get into it, but I did a very simple Nikolai type calculation of the takeoff distance, roll distance required with that amount of thrust, and it came out to be 7,700 square feet, and you can, which is fairly reasonable. Okay, now wing. Well, we've talked about the body, the fact that the body really for hypersonic reasons, we'll talk more about why it's shaped like it is for hypersonic reasons later, but it also produces quite a bit of lift. Now what about a wing? If you could focus down here, please. Wing is not required for takeoff unless you have to operate at a reduced takeoff velocity or a smaller angle of attack. But there is stability considerations that have to be considered. There's a high-speed vehicle stability that's established by what's called an unstable short period oscillation. Okay, this is a longitudinal oscillation. What it basically is if you have some kind of an oscillation in the plane, if it's unstable, the amplitude will increase in time. And what vehicle management people or stability and control people are concerned about is how much time does it take for that amplitude to double in size, okay? That's what is called a time to double amplitude. Now, if that time to double is greater than 0.3 seconds, it can be handled by active controls. Shown below is an equation for that time to double that is a function of the Cm alpha or M alpha, that's a partial derivative of moment with respect to angle of attack, divided by the moment of inertia of the body. Okay, so we're going to look at this at Mach 15 for our baseline vehicle. Mach 15, a dynamic pressure of 1,500 pounds per square foot. Our planform area came out 5,000 square feet. And the first step is determining what the moment of inertia. So I assumed a fairly simple model for the area distribution, just linear, going to the maximum value at wherever it occurs. Down below that, if you assume that, you can actually calculate equations for the center of gravity and the moment of inertia as a function of a couple of key parameters. And for our vehicle, the CG came out to be at 53% of the length back from the nose, and the moment of inertia is shown down here below, basically 3 million slug foot squared. Okay, I also showed the maximum area and the average density of the vehicle, which will all factor into this. Now what about that moment derivative, that partial derivative of moment with respect to alpha? Using that moment of inertia that we calculated for our vehicle, it says that the m alpha has to be less than or equal to 18 million foot-pounds per radian. Okay. Now this analysis we're going to talk about quite a bit later. This was Zane Pinckney at NASA Langley running nose-to-tail, essentially CFD solutions for our baseline vehicle and a lot of variations. From this data, it showed that the m alpha was 36 million foot-pounds per radian, which exceeded our limit by a factor of 2. Now, one way to decrease that m alpha is to put a wing aft of the center of gravity. Just think about that a little bit. If you put a wing back there, it shifts your center of pressure aft, and it produces a pitch-down pitching moment, okay, which will help that m alpha. I also looked at a power-off analysis to make sure that if the engines were to be turned off, that the power-off point wouldn't be more critical than the power-on, and it was not. So power-on is our driver for this case. Looked at the wing, did a lot of iterating on the wing, found out that to make for this huge partial derivative moment with alpha, which I'll explain a little later why it was so large, and it really won't be that large if you have a high-performing flow path. It either required a huge wing or a thick wing. And so I sort of compromised, and I picked a 5-degree half-angle wedge airfoil. This is sort of reminiscent of what the X-15 had to do to maintain directional stability with its. If you go down to the Air and Space Museum, you'll see that big wedge on the tail. Same kind of thing, okay? This is just for longitudinal stability, okay? From oblique shock theory, which you probably heard about yesterday, the CL alpha of that wedge would be 0.126 per radian. For a delta wing aligned with the trailing edge of the body, let's just show that again. Here's our delta wing. That's just an assumed shape for that wing with the trailing edge aligned to the back of the plane. You can get a moment relative to the CG due to the wing that is derived as such. And differentiating, that's a function of the lift of the wing. Differentiating that, we get a partial moment with respect to alpha of the wing being a function of the lift curve slope, change in lift with respect to alpha, and some geometric parameters. Okay, and the result is down at the bottom. Here I should point out that the moment coefficient is relative to the planform area of the body and the length of the body, whereas the lift coefficient is relative to the wetted area of the wing. So you don't get those too confused. There's also an additional contribution to the wing, which has to do with increasing the moment of inertia. The higher the moment of inertia, the lesser the problem. Well, the wing is a lot of mass after the CG, so it increases the moment of inertia of the body. So there's an effective CM alpha due to that wing. And using simple, geometric relationships, you can calculate what that moment of inertia is. It is a function of that unit weight, which I said we used was a value of 3, and I kept it the same for the wing for lack of other information. It's also a function of the wing sweepback angle, which was another thing that I compromised on a little bit to keep the wing a reasonable size. Okay. Our required M alpha from the wing turns out to be minus 18 million pounds, which in terms of CM alpha is shown here as 0.016. Adding the two components, the effective and the actual CM alpha, together and iterating on the wing size, it turned out we had to have a 1,900 square foot wing with a sweepback angle of 73 degrees, and that angle was chosen so that the wing leading edge wouldn't move forward of the body midpoint. So that's, again, now we've put a wing on our design. That wing isn't there necessarily for high-speed lift, and definitely not for low speed. It's there for high-speed stability. Okay. If you could show the bottom of the chart here, this wing size could be reduced by sharpening the nose plan form. I'll refer to this, putting a triangle in there, or just somehow carving off some of the nose. That reduces the pitching moment of the forebody. That would be one thing that would help. Increasing the scramjet performance. The actual baseline shape that I've got here and the way it was operated had very low performance, as you'll see later, and it decreased pretty rapidly with angle of attack. So as we went to higher angles of attack, the thrust fell off. In other words, the force is acting on the aft end of the vehicle on the nozzle. If this is our nozzle back here, we're dropping off very radically. The forebody pitching moment was increasing, but the nozzle lift was decreasing. That's what gave us this big CM alpha. If that performance was improved and you had a different behavior with angle of attack, you'd help yourself out tremendously. And you'll find later that was indeed the case when we refined our configuration a little bit. So now we've got a large wing. It could be used to reduce our takeoff velocity or angle of attack. One other aspect that gets into the wing sizing is longitudinal control. A typical parameter used to establish a control requirement or a control power is something called control volume, which is basically just the planform area of the control surface times its distance away from the CG divided by the reference planform area, which is our body planform area and length. Okay. A typical value that can be used for preliminary estimates of the control power requirements is what we call a V-bar, or control volume requirement of 0.04. Back when I sized the wing, another thing I did was took some liberties with the center of gravity. I moved it up to 50% to help out the problem, instead of the 53% that the body would have been if it had a uniform distribution of density. That can be achieved by packaging the thing differently. It might be a challenge, but it's something you do have some flexibility over. In any case, using this V-bar requirement of 0.04 results in a 400 square foot elevon requirement for control. So with our wingspan that came out of our wing, gives us a chord of 8.3 feet. And that again is shown in our preliminary design down there. Okay, we've sort of gotten through the primary low-speed drivers. We're going to move on to transonic drivers now. Big transonic drivers are the transonic drag rise. That's a function of the fineness ratio of the vehicle and the distribution of area. Those familiar with area ruling are familiar with that phenomena. Inlet drag is very important. It can be very big. Body ramps are required for high-speed inlet efficiency, and at low speeds it therefore creates a lot of drag, a lot of what we would call spillage drag. Also nozzle drag. The base area of the nozzle is very large. It's required for high-speed thrust, as you'll see later. If you didn't have that, you would have very low high-speed performance. But at low speed, you have very low, what's called nozzle pressure ratios, a low ability to fill up that nozzle with high-pressure air. And so you end up with sort of a base region that can be very high drag. The changing physics of drag with Mach number, sort of interesting. At transonic speeds, I mentioned, it's a function of fineness ratio. The basic physics of the flow, if you move up a little bit, the flow is linear to small perturbations, and drag is a function of area distribution and fineness ratio. Moving down, lower on the bottom of the page, hypersonically, the flow is very nonlinear. Disturbances are quite localized with steep Mach waves. And drag is really primarily a function of local surface inclination angle, and that's sort of illustrated by the Newtonian theory that drag is proportional to sine squared delta, or pressure, CP, either one. So high speed, all you need are small deflection angles, Transonically, you want low fineness ratio. Well, our vehicle has, come back to our vehicle here, has quite shallow deflection angles, but it's not necessarily a real high fineness ratio. Okay, transonic inlet drag. I already mentioned that the ramp and inlet systems are typically generate large drag at transonic conditions. They're there to provide high efficiency to the engines at high speeds. Therefore, the ramps are large, they're fairly steep angles. Another point is that at high speeds, the inlet throats must be small. I mentioned that earlier. Contraction ratio has to be sufficiently large to reduce the Mach number and increase the pressure of the gas. And the size of the throat at low speeds is limited by mechanical considerations and your ability to fuel that big depth of air. So you can only open up that throat so much at low speeds. If you could collapse all those high-speed ramps, it'd be great because you'd reduce that drag, but that's very difficult to do in practice. This sort of shows the physics of the flow transonically, where you get supersonic compression against along some of the ramps to the point where you would have a detached shock. And then as you try to push that flow through the inlet, typically your throat area will be too small to allow this last shock to be supersonic, and you actually end up with a bow shock out in front and what we call subsonic spillage, which really increases the pressure on those wedges and increases drag dramatically. Okay, I'm going to have to speed things up a little bit. I might have to skip some of this. Just wanted to point out that from some data I got from Pratt & Whitney, courtesy of Don Stewart, the maximum contraction ratio you can operate at is a function of Mach number, where at very low Mach numbers, you can't contract the flow much at all. Okay, if you try to over-contract it, the inlet will unstart. We talked about unstarts earlier. At higher Mach numbers, you can go to higher contraction ratios. This curve is typically, I use like the center curve to establish the contraction ratio versus Mach number limits for our design. I did just to quantify what these drag levels might be, I did an analysis for our design. Our design was laid out to have a shock on the lip. It means that the bow shock of the vehicle is on the cowl lip at Mach 15. Okay? Then I compared that to a Mach 18 design. Okay? At Mach 18, the shock is closer to the body, so the cowl lip is closer to the body. Okay? So for the Mach 18 shock on lip design, since the cowl lip's closer to the body, the ramps can be shallower, and it will typically generate lower transonic drag, and you'll see that here. I did this analysis using a program that we call SPIL at Rockwell. It deals with the multiple ramps and inlets. It does account for viscous losses, and it does account for that detached shock and subsonic spillage that I pointed out. The cowls were geometrically lowered in our design to the point where the internal contraction ratio was 1.2. Okay, that's going from the cowl lip back to the throat. Any more than that would not allow the inlet to start to swallow all those shocks at a point where you might want to operate the engine in a ramjet mode. So I wanted to get it down to at least that level. Okay, so for the two designs, the baseline and the shock on lip of Mach 18, this shows you the difference in that ramp drag, 125,000 pounds compared to 108, and the ramp lift. That's 500,000 pounds versus 550. Now these are huge numbers. In fact, our plane doesn't weigh anything like this. What it tells you is that at transonic conditions, with that strong negative camber, you wouldn't want to fly at 0 alpha. You'd actually want to decrease the angle of attack to reduce the lift and make it fly in equilibrium. Later we'll show how, even though transonically this was a benefit, decreasing that cowl hurts you hypersonically. Okay, nozzle. The nozzle region also typically generates large drag at transonic conditions. I already mentioned why a little bit. The large areas are required for high speeds. The engines can't generate a very high pressure ratio, so you can't fill up that nozzle area with high pressure air. This is some test data that was generated at Lockheed and reported in the literature. showing at transonic, well, this is really subsonic, but it's sort of at the beginning perhaps of transonic, Mach 0.6. But the phenomena is the same, Mach 1 or 1.2, showing pressure distributions on the aft ramp. As you can see, there are large regions of negative pressure coefficient, which contribute to drag. This is sort of an interesting plot here. This shows the ideal nozzle area divided by the base area of our vehicle. Okay? The ideal area is defined as the area that the propulsive stream would take up if it were to expand isentropically to ambient pressure. Well, you can see down here in this turbojet regime where we're operating our turbojets, we only fill up maybe at most, even at Mach 2.5, 10 or 15 or 20% of the nozzle area. Okay? Eventually, there's our 1 value, somewhere around the higher ramjet mode, we fill the entire nozzle, and then above that, we are actually underexpanded. Even with a large nozzle, we haven't expanded it all the way back to ambient conditions in the scramjet mode. And this is what drives that area to be as large as it is the requirement to try to get as much work energy out of that flow as possible. Okay, I'm just going to get to the point here because I'm running a little bit behind. But for our 2 engines, we basically expand out to only 10 square feet of area. Okay, but our axial projected area is 400 square feet, so that provides a lot of base area. And just using a sort of a flight test data based pressure coefficient with Mach number, that results in an estimate of nozzle drag of 166,000 pounds, which is more thrust than even 4 engines would produce. So that's more drag now than we have thrust from our engines. Also briefly, this just shows how 2 of the nozzle variables impact that nozzle drag, nozzle thrust. This is in terms of a nozzle gross thrust coefficient, which is just a measure of nozzle thrust. I'll talk more about that, what gross thrust coefficient is later. But what it shows you is that, remember that chordal angle I talked about, that average angle of the nozzle? As you increase that angle, the thrust goes down at low speeds. And that's this one, I'm sorry, this line here is with chordal angle, and then the lower line here is for area ratio. You increase the area ratio, decrease nozzle drag. Increase the chordal angle, decrease nozzle drag, and vice versa. Just one of the drivers in the design that you have to be aware of when you're designing the plane. Now, one of the, Dr. Lewis mentioned the possibility of burning externally. Well, this is one means that you can alleviate that transonic drag, is to add fuel external to the engine, cowl, and burn it to fill the nozzle region with hot, low-density gases at ambient pressure. In the case where you don't have that, you can see what's happening. The engine cannot fill up that base, so the flow coming around the cowl has to expand. The angle is, this is an obvious expansion corner. It looks like an expansion corner. It expands, and the pressure drops below ambient in this region. Well, if you can inject fuel, burn it, and fill that region with ambient pressure, high-density air, you can alleviate that transonic drag. Chuck Trefny at NASA Lewis has done a lot of work in this area, both experimentally and theoretically. And using a little one-dimensional design code that he has, I estimated how much hydrogen would be required to eliminate that base drag, the transonic base drag. And these are shown as a function of Mach number for Mach 1.2, 2, and 2.5 for our vehicle. And these are the hydrogen flow rates in pounds per second required to eliminate the drag theoretically. As you can see, as Mach increases, the nozzle, the engine fills more and more of the nozzle to the point where you would no longer have to rely on external burning. Okay. Now, just briefly, the transonic drag and specific impulse of our baseline configuration. You can work through this. I used standard aerodynamic procedures in design books, like Nikolai was used here, to evaluate the drag of our vehicle at Mach 1.2. Drag's made up of friction drag, pressure drag, base drag, which I've just told you we've driven to 0, and then wave drag. Pressure drag being different than wave drag, just this is more like separation pressure drag. So using the methods and the conditions we're operating at, get different, the wave drag comes out to be the D over Q 39, value of 39. Let's walk you through this very briefly. We're able to evaluate the pressure drag contribution, and the total zero lift drag came out to, in terms of drag over dynamic pressure, was 58. Okay, assuming our plane has used a little bit of fuel and now weighs 145,000 pounds, our lift over Q is 145. In reference 7, which is Nikolai, there's a figure that shows experimental data for the drag due to lift factor K, which is the derivative of drag with respect to CL squared. And for our vehicle, about 0.45 is the value. So from that, we can evaluate the drag due to lift of our vehicle, and the net result is our plane produces about 60,000 pounds of drag at Mach 1.2. Okay, obviously operating at a negative angle of attack to get that, because we showed before that the lift and drag on the ramps at 0 alpha were quite a bit higher than that. Okay, down below I just show what our vehicle ISP would be. You can think of engine ISP as being the thrust of the engine over fuel flow. Well, the whole vehicle has a characteristic ISP as well, which is the engine thrust minus vehicle drag over fuel flow. And that vehicle or effective ISP is what establishes ultimately the amount of fuel that's used. So combining, first of all, looking at our 2-engine package, we note that there is not enough thrust transonically. If we choose 3 engines, we'll get the same acceleration we got at takeoff, which seemed like a reasonable level, okay? But when you combine that with the external burning flow rate, we get an effective ISP of only 490 seconds. That's only marginally better than a rocket without a vehicle attached to it, okay? So what I did was, to bring that ISP up, I added an additional engine. We've got 4 turbojet engines on our vehicle. That increases the thrust, and the net effect is an ISP of 760. I left it there, but you can start to see the trade-offs here between, we've added more engines, more weight, more dead weight to orbit, but it was required to satisfy the transonic pinch point. We've used external burning to try to mitigate that drag effect. Really start to see how all the pieces come together here and interplay. I'm going to move on to supersonic drivers. We've gotten through transonic now. Supersonic drivers are inlet operability. That means starting the inlet. We talked about requirements to start the inlet. Contraction ratio cannot be too large or it will not self-start. You have to geometrically do something or dump air or have blowout doors or something like that to start it. And then unstarting, that was also mentioned. That the tendency of the engine, the combustor can force an unstart. A number of things can unstart the engine. Combustor inlet interactions, that's really what I just talked about. Trying to isolate the pressure rise in the combustor. That pressure rise in the combustor is just like an adverse pressure gradient to the boundary layer. Remember, we've integrated our engine onto the airframe. And so all that boundary layer air is coming into the engine, and it sees that adverse pressure gradient in the engine. If you're not careful, that can cause interactions to feed upstream, boundary layer separation or whatever mechanism to feed pressure upstream, and you don't want to feed high pressure upstream on your inlet ramps, because that's aft facing area and that's drag. Thermal choking is an issue, adding so much heat to the flow that it hits Mach 1 before you've added all the heat. Hydrogen air kinetics, in terms of ignition delay, Dr. Lewis already mentioned some of this, and your ability to hold a flame. I can't develop that too much, but flame holding is basically having a low-speed recirculating region where you can support a hot, slow-moving gas and support combustion. Combustion efficiency, it's tough at these low speeds. Remember, our contraction ratio was low, so our depth is high. And how do you get fuel out there? Well, you either got to stick things out there or try to inject it from the wall. That's tough. and the issue of thermal versus mechanical choke. In the ramjet mode, you need to choke the flow before it goes into the nozzle, and there's two ways to do it. One's adding heat and thermally choking it, and others to mechanically vary things and have a physical or mechanical choke. Ramjet to scramjet transition. Where does it occur? Where should it occur? Where is it optimal to occur? That's a pretty complex issue, actually, as it turns out. It's a function of many variables. Cycle efficiency, where it's more efficient to do it to operate as a scramjet. Inlet temperature limits. If it's too high, you'll dissociate your burned fuel and lose thrust. Pressure limits. Structurally, if your pressures get too high, your engine weight gets higher, so you're practically limited there. And thermal choking. I did an analysis, an investigation, assuming an inviscid perfect gas analysis on something called an Oswatich inlet. An Oswatich inlet, we'll talk about more later. It's the inlet design I used here. It's basically having turns on the forebody and ramp that have equal total pressure losses. It defines a theoretically optimum inlet design. Okay. That curve I showed you of maximum contraction ratio versus Mach number was used, and I didn't know if this transition point might be a function of how many ramps, so I looked at 3 ramp, 4 ramp, and 5 ramp systems, and in the analysis 1D constant area heat addition was used. Now, getting to the conclusions before I show you the plots, it indicated a transition of about Mach 6.5, and that was dictated more by the constraints than on the cycle efficiency. And I did find that the results were insensitive to the number of inlet turns, and I also found that a divergent scramjet would be required from Mach 6.5 to 10. You couldn't have a constant area because you'd thermally choke the flow, wouldn't be able to add much heat to it. Okay, this shows the results. It's a total pressure ratio to the end of the combustor as a function of free stream Mach number. The ramjet points are the squares, and the scramjet points are the crosses or the pluses here. And it's interesting that from a thermodynamic efficiency point of view of total pressure loss, the crossover from ramjet to scramjet didn't occur until about Mach 11. You could actually thermodynamically operate the ramjet up to that region more efficiently than the scramjet. Plus, the scramjet below Mach 10 was choked in a constant area. You couldn't add that much heat. If you tried to, in a constant area section, you'd have upstream interactions, and you'd probably unstart the inlet or something like that. So it would require, for Machs, about any time you did start the scramjet on up to about Mach 10, to have some kind of divergence in the combustor, which we don't have in our design. It's a limitation of our design. This shows the combustor exit Mach number after adding the heat as a function of free stream Mach number, and this is that thermal choke I talked about. You see, you don't come off of that Mach 1 until you get to Mach 10. Subsonically, you never reach a Mach number of 1. Now it really came down to these constraints or limits. If you picked a reasonable pressure limit of 10 atmospheres in the combustor, you cannot run that ramjet higher than about Mach 6.5, maybe even a little less, before you exceed that pressure limit. That's not a hard limit. That needs to be traded, that weight versus performance, but it's a reasonable kind of number. So that's one limit, and then the other is the inlet temperature limit. If the inlet temperature gets too high, you'll dissociate all the water you're forming, not all of it, but a large fraction of the water you form when you combust, which will make you lose a significant amount of thrust. A reasonable one from experience is 3,500 degrees Rankine, which again establishes that crossover or limit to be about Mach 6.5 for transition from ramjet to scramjet. Okay, that's one of the primary issues in the supersonic regime. Supersonic regime tends to be a fairly insensitive regime from the point of view of performance, but you do have those operability issues of starting the inlet, keeping it started, not unstarting it, adding heat to it. I've pretty much covered those. We'll move now to hypersonic drivers. There we're driven strongly by vehicle drag, the ability of the inlet to capture a lot of mass, therefore produce thrust. Thrust is just proportional to mass capture. the compression efficiency of the forebody and inlet, in other words, low shock and viscous losses, combustion efficiency, which is driven by your ability to mix fuel and air, and any losses you have in the combustor. Nozzle efficiency, there are a lot of components of that we'll talk more about later. Boundary layer transition, aerodynamic heating, moving down. Flow path heating and active cooling in the flow path. We'll see that regenerative cooling, that's taking your fuel, using it to cool your surfaces, adding heat to the fuel, and then injecting it hot is a not good thing to do. It helps performance, and it's actually required. Stability and control we already talked about. We've looked at that and sized our wing because of it. And then trim drag. That can be big if your plane doesn't balance out moments by itself, then you have to have your control surface do it, and that introduces drag. This is a very interesting plot here. It shows a ratio of the energy in your fuel. If you move slightly to the left, yeah, fuel energy divided by kinetic energy of the flow. Okay, that ratio. Well, at low speeds, the fuel energy of hydrogen is tremendous, so you get a very large ratio. As you go to higher and higher velocities, or Mach numbers, up to orbital speeds, you get to the point where the energy content of the specific energy of the fuel is about the same as the specific energy of the air. So adding heat to the flow is a perturbation problem. You're perturbing the flow. Things are much more sensitive. Dr. Lewis talked about that the eta KE, or the inlet efficiency, was always about 0.97, and the nozzle efficiency will be similar. It'll always be a very about the same number, not varying by much more than maybe 1%. The reason for that is you're at such high velocities, you don't change the velocity much through the flow path, and he illustrated that. Velocities do not change much. You don't hit the flow very hard to increase its pressure and do all the things thermodynamically you want to do through the engine and flow path. And that's why it makes the high-speed performance also very sensitive to how good an efficiency you have. Okay, aerodynamic considerations versus Mach number. We've already discussed all the low-speed ones. High speed, we talked about that the high-speed drag is a function of local surface angle. It's also a function of boundary layer transition. Another aerodynamic consideration is heating and cooling. Balance between propulsive performance and your requirement to provide some lift. Already talked about flow uniformity and the flow quality to the inlet, and stability and control, including directional stability, which I won't talk about too much. Okay. Touch on boundary layer transition a little bit. Transition from laminar to turbulent flow is driven by a number of physical phenomena. One is just basic flat plate phenomena, Tolman-Schlichting modes, disturbances that become amplified and eventually go nonlinear and transition the flow to turbulent. The first mode, or Tolman-Schlichting mode, is a dominant mode for transition at low Mach numbers, roughly less than 7. The second, there's a second transition mode that becomes dominant for cold walls at higher Mach numbers. Our walls are typically going to be cold. They can't get too hot or they'll melt. A typical transition criteria for just flat plate type transition is a Reynolds number based on momentum thickness, RE theta, over local Mach number, being in the range of 150 to 300, that determining the kind of where transition would occur. Something that you can delve into is this fairly recent development, stability theory, or E to the N theory, seem to be very good at predicting flow transition in quiet flows, flows that don't have a lot of free stream turbulence, like in free stream. Another driver is cross flow. Okay, that's just flow. Let's say you had your wedge and you had flow transverse to the wedge. That's cross flow. Here, the transition is driven by a Reynolds number based on the cross flow velocity. These are typical numbers for that. Attachment line, like on a blunt leading edge, you have an attachment line. That is driven by the span-wise velocity along that edge and the momentum thickness along the edge. We'll go ahead and stop there, and we'll pick up more on flow transition after the break.